In this video, we're going to start with one practice problem in terms of just performing the calculations for in calculating the midpoints, the apparent limits, and real limits, as well as calculating the lowercase I, the interval width. And so in this question, the ask here is to create a frequency distribution, at least in terms of calculating the limits for the height of 450 professional football players. The tallest player was found to be 229 centimeters, and the shortest is 173 centimeters. And so the first question is to ask, what value do you select for I? And then what's the midpoint value for the first or the lowest class interval? So the first step here is to calculate the range. And so the range is computed from the single highest score, subtract the single lowest score. So we have a range of 56 centimeters. Now, we then determine I by dividing by n intervals, so 10, 11, or 12 intervals. So we first start with 10, in which we come up with 5.6, and then we divide by 11, so there's a little bit of trial and error here. And so since we divide 56 by 11 and we get 5.1, we're going to go with 5. The lowest midpoint we determined to be 175. And so the way we determined 175 is that it's a value close to the very smallest value, and it's going to be a multiple of I. And it should be a number that's relatively close to the lowest score. So remember, we want to go with our value for I to be with 5. We don't get exactly 5, but we keep working through our calculations until we get to a value that is odd and is close to the whole number. And so we take the multiple of I until we get close to the lowest value of 173, and that's 175. We then calculate the apparent limits, which is the first midpoint, or rather the lowest midpoint that we first computed, 175. We put 175 as the midpoint, and we add and subtract 5 minus 1. Remember, I is equal to 5. We didn't get exactly 5, but we have to round to the closest value. So 5 subtract 1 is a 4, divided by 2 is 2. And so we add 2 to the lowest midpoint, which is 175. That gives us 177. And we subtract 2 from the lowest midpoint, which is 175. Subtract 2 is 173, giving us our apparent limits. We then compute the real limits by adding and subtracting 0.5 from the highest value and lowest value respectively of the apparent limits, yielding 177.5 and 172.5. So our next example is quite similar here, but we're going to examine body weight distribution of professional football players. And so we have 32 teams, and if we estimate 70 players per team, giving us a total of 2,240 players. In other words, 2,240 data points. The heaviest player was measured at 335 pounds, the lightest at 181 pounds. First step is we need to determine the intervals by first calculating the range. So we take the highest value, subtract the lowest value, giving us a range of 154. Now, we want to determine I, which is the range divided by n intervals. Remember, we want I to be an odd number. So we start with I is equal to 11, and we arbitrarily selected 11. And that will give us 14 class intervals, which is a little bit high. We then divide I we set I to 13, that will give us 11.8 class intervals. We do this one more step. We set I to 15. When we set I to 15, we're widening the interval, creating less intervals. And so we have 10.4 class intervals. Now, how do we make a decision on how many intervals to use in our grouped frequency distribution? Is that we see that 10.4 is closer to 11 than 11.8, so we'll set to 11 intervals. We then calculate the lowest midpoint, and the lowest midpoint must be a multiple of 15, since that's the I we decided to go with. And so we try 15 times 11, that gives us 165. Remember, our lowest weight was 181, so this estimate was too low. We try 15 times 12, which gives us 180, which is very, very close to 181, and that's just right. That's the interval that we want to start with at the bottom. We then calculate the apparent limits around the lowest midpoint. And so it's the midpoint value plus minus I, which is 15, subtract 1 divided by 2. So that gives us 15 minus 1, which is a 14, divided by 2 is plus minus 7, and that will give us our apparent limits. So we have 187 and 173. So 180 minus 7 is 173, and 180 plus 7 is 187, and that sets our apparent limits. And once we have our apparent limits, we can then add and subtract 0.5 to set the real limits at 187.5 and 172.5. Remember, the plus and minus is applied to the highest score in the interval, and to the subtraction is applied to the lowest score in the interval. So this is a table, this was already sorted through, where the frequency, the number of players that fell within the established real limit intervals, you can see here. So 128 players fell within the lowest interval category, 320 players, 288, so on and so forth, and this continues up until the highest frequency of 64 players all fell within the real limits. And if we go to our frequency, and this was something we observed in a previous video, in the previous part of this unit, that if we go to the frequency column and we add up all of the numbers vertically, they should add up to the total sample size that we had at the very beginning, and this works out. We now move to including the other columns in our frequency table. So we have our frequency, we establish the midpoint, we establish the apparent limits and the real limits. Recall, we started this process at the very bottom with 180, and then we just continue to add 15 all the way up until we get to an interval that is close to, that captures the single highest score. What we now add is a relative frequency and cumulative frequency and percentile columns. And so what we see here is a similar step that we had before. We had in the very first row, in the first interval, we had 128 players. Well, in terms of the accumulation of the number of players, we have 128. Now, we take the 128, we add it to 320, and that will give us a cumulative frequency in the next row of 448. We then add 448 to 288. It gives us 736, and we continue this process until we get all the way to the top. And when we get all the way to the top, what we see is we have a cumulative frequency that equals the summed value at the bottom of the frequency column. And so We then compute using the equation presented in a previous video. We then compute the relative frequencies that occur as a percentage. So 64 divided by 2,240 expressed as a percent is 2.9. 128 divided by 2,240 is 5.7. And we continue this all the way through until we get to the bottom. And when we add up all the relative frequencies, it should add up to 100. Now the percentage of time the scores occur is what we're looking for here. And so we start with the 128. We see that 128 out of 200 divided by 2,240 is equal to 5.7 percent, and we express it as a percent. It is reasonable to have left this as a ratio value without multiplying it by 100%, but the percents are usually better, a little bit easier to interpret and understand. Now, in terms of computing the percentiles, as you can see in this illustration, or in this final column of the graph, the percentile is similar to a cumulative frequency and represents the percent of all scores at or below the score. So the players that fit within the 100 percentile are at the very top of the weight magnitude, as 100% of the weights exist at or below this at or below these real limits. So for example, if we go to the real limits of 247.5 to the 262.5 pound interval, it sits at the 68.6 percentile, suggesting that 68.6% of all player weights exist at this and below this interval. And so in order to compute the percentile, it's just simply the cumulative frequency divided by the summed frequency at the bottom, and the value is entered into the percentile column. For example, if we take the cumulative frequency at the very top, 2,240, divided by 2,240, that gives us 1 times 100 as at a 100 percentile. So once we have this, we can now begin to take a look at a closer view of these data by applying this frequency distribution. So for example, if we were interested in players that had a weight at the 30th percentile, if we know what the percentile is, then what we're going after is the raw score in pounds. Alternatively, if we're provided the raw score in pounds, then what we need to determine is the percentile of that raw score. And so this is a prescribed formula that you see here, where CF refers to the cumulative frequency corresponding to the percentile score. And so this is information we'll get from the table. And so the percentile score is a given here at the 30th percentile. Okay, and just as a review, that's the percentile rank times n divided by 100, where n is the total number of scores. Fi is the frequency of the class interval containing that cumulative frequency. LRL is the lower real limit of the class interval containing that cumulative frequency. I is the class interval width, which we calculated as one of the first steps here. The UL is the CF, the cumulative frequency in the class interval below, under the limit, so below the interval containing the cumulative frequency, and we'll take a look at this here on this graph. So if we're interested in calculating the body weight at the 30th percentile, we can kind of take a look through this table, and what we see here is we see the 30th percentile is not exactly captured. It's below 32.9, but we want a single value for the weight at the 30th percentile. And so the cumulative frequency is, by following the formula, is 30, because that was a given, times 2,240, all divided by 100, and now we have a value of 672 that we would put into the cumulative frequency. So as we can see here, a value of 672 does not exist here on the table, but explicitly, but it's implicitly between these two values that we need to determine that weight somewhere between there. The lower real limit, so this is the row that we've identified. The lower real limit is what we obtained from the table, so 202.5. The Fi, the frequency at that interval, is 288. And then the only time we move off of the row is for the UL value. And that's the cumulative frequency right below. So we're basically taking a difference of these frequencies so that we can get to the 672 value. So in working through these numbers, we're just going to substitute these values. So the lower real limit was 202.5. We're going to add that to the quantity here where we take the 15. We multiply that by the difference between 672 and 448, all divided by 288, and we find a final value of 214.17 pounds. So a player at this weight is sitting at the 30th percentile. And so using frequency distributions to determine percentile from a raw score is something that we'll focus on next. And so here we see the cumulative percent of these scores, where at the very top end it should be 100, and that's exactly where we are. And that indicates that at a weight of 337.5 pounds, 100% of the players have a weight at or below. And as we see, as we move to lower and lower weights, less and less players account for the number of players in that category. And so if we were to plot this, we would use the upper real limit to do so, and we always close our polygon at 0. So now the next question here is to calculate the percentile. So if we have a player that comes in into a team at 305 pounds, we want to determine what's the percentile of that particular player. And as we saw on the previous approach in computing a raw score from a percentile, this is a prescribed approach in which we use the equations. This is a new equation to determine what that percentile rank is, where CF, once again, is the class interval below the interval containing X, which is the raw score. X is the score of interest. Okay, and so this is what we have here. So this was a given, and we're calculating the percentile rank. LRL is the lower real limit of the class interval that contains X, so we know what 305 is, so we're looking for that in terms of the real limit capturing of this weight. I is the class interval width. Once again, we did this at the very beginning. Fi is the frequency of the class interval containing X. N is the total number of scores. So we want to calculate the percentile rank. Now this is going to represent your first seminar practice problem. So I'm going to leave this problem to you here. This is not something you're going to hand in, but this is something I'd like you to attempt before your seminar next week, where the TAs will work through the solution to this question.